all. Today's lab is operational amplifiers. So the purpose of this experiment is to examine the properties of the operational amplifier and to learn how to design practical op-amp circuits. So in this lab, we gonna to introduce or we gonna to see the concepts and equations of inverting and non-inverting amplifiers. What's amplifier? What does amplifier mean? Or operational amplifier. Operational amplifier, typically called op-amp for short, is an active circuit element designed to perform different mathematical operations on electrical signals like addition, subtraction, multiplication, division, differentiation, and integration. Op-amp is a versatile circuit building block, acts like voltage-controlled voltage source. In a combination with other elements, it can be made into other dependent sources like voltage or current controlled current source. An op-amp can sum signals, amplify signal, integrate it, and differentiate it. So op-amps are popular in practical circuit designs because they are versatile, inexpensive, easy to use, also fun to work with. The op-amp is an electronic device consisting of a complex arrangement of resistors, transistors, capacitors, and diodes. There are different types of op-amps or commercial available types of op-amps, but we are in this lab or we are going to work with uh, 741 general purpose op-amp. So from its name or from here we can see this is the op-amp or the one that we are going to use, which is 741. 741 uh, from from the name. So what does 741 mean? Also, as you can see here, there are 8 pins for this op-amp. Only 7 pins are active. So this is number 7. What does 7 mean? Only 7 pins are active. And the initial IC simply means that the op-amp is made inside an integrated circuit. So op-amps have a total of 8 pins, and out of those 8 pins, one is inactive, which is pin number 8. This one. You can first let me show you one thing to know the number of these legs. You can see this is the black circle. So from this black circle, which is uh, upper left corner. So this is pin number 1, 2, 3, 4, 5, 6, 7, 8. The last one, which is this one, is 8. This one is inactive or is not connected. 4 of these pins, which are 2, 3, 4, and 7, supply the input, and one of the pins, which is pin number 6, is the output. So 7 means 7 active pins, 4 means 4 inputs, and 1 means 1 output. Here, also, 7 pins are active, but we are going to work only with 5 pins. Two pins are used for null offset, which is out of our box. So we will work with the pins which are used for null offset are 1 and 5. Pin number 2 is for inverting input. 3, non-inverting input. 4 is to supply the negative, is for the negative supply. 5 is, as we said, is out of our box, which is used for null offset. Uh, Usually, when we say that, it's used to calibrate our op amp if it has offset, but it's out of our box. So pin number 1 and 5 are out of our box. Pin number 2, inverting input. 3, non-inverting input. 4, to supply for negative supply. 6 is your output. 7 for positive supply. A is not connected. You can see here for each one for inverting op amp and for non-inverting op amp, each one has its gain. So there is a difference between the open loop gain and your amplifier gain. Your amplifier simply your gain is output divided by input. And you can see here, this is, if you read the sheet, you can see this is your voltage gain, which is V out divided by Vs or V input, which is, R2 divided by R1. This is the open loop gain. And for non-inverting op amp, this is your gain. 1 plus R2 divided by R1. Here, when we say inverting op amp, this means the phase shift between the input and the output is, there is a phase shift between the input and the output 180 degree. For non-inverting op amp, there will be no phase shift. So this is our op amp. So we are going to work with this op amp as inverting and non-inverting. Now we can start our experiment with the first part, which is we are going to start this experiment with inverting op amp. So we will build this circuit, this one, which is inverting op amp. So we will use 3 resistors. This R2 is your feedback, which is connected between the input and the output. And this is your input resistance. The op amp has, high resistance. That's why the voltage difference between 2 and 3 is 0, or no current will flow through this op amp because this op amp has 2 very high, or this means our current or the current flowing through this op-amp is almost zero, or theoretically we are considering is at zero as zero. So we will work with this one as our first part, which is inverting op-amp. Now, let we start building our circuit. But as any experiment, we should start by measuring our resistors. Now, this is R1, so we should, measure and record our resistors because we are going to use to find our gain. So R1 theoretically is 5.1 kilo ohms, and practically we got it as 5.05. This is R1. R2 theoretically 20 kilo ohms, and by measurement it's 19. First one, R1, is 5.05 kilo ohms. R2 is 19.82 kilo ohms. And we know due to tolerance, we cannot get exactly the same. But it's within the tolerance, so that means they can be used. R3 is 5.02 kilo ohms. So after measuring these, we can start building our circuit. Here you can see R1 is connected to pin 2, so it connects your supply or your wave generator or waveform with R2 with pin 2, which is inverting input. And R2 is your feedback resistor, which is between 2 and pin number 6. R3 is connected to the pin 3, which is non-inverting, and then to ground. This is positive PCC, which is pin number 7, negative PCC, pin number 4. So we are going only to use 5 pins. Now let we start building our circuit. This is R2. R1 is connected to pin number 2 and to your analog wave generator. I have choose channel 1. R2 is between, let me just move it here. R2 is between 2 and 6. So R3 is connected to pin 3 and ground. Now we have connected our resistors. So this is R1, R2, R3. R1 connects your analog wave generator, and pin 2 or which is Ri or R input. R2 or your feedback resistor is between pins 2 and 6. R3 is connected to pin 3. Now we have to supply our op-amp with positive and negative voltage. So this is the negative is to pin 4 and positive to pin 7. Also, we need to connect our input to scope. Let me choose channel 1, and our output to the scope also channel 2. So now it's ready to be used, right? This is the negative supply to pin 4. This is the positive supply to 7. This is channel 1, which is your input, channel 2, your output, and now we can start our experiment. So first, we have to supply our op-amp with 9 volts, and we are going to limit the current to 900 milliamps. Also, we are going to supply the op-amp with positive and negative for DC voltage, 9 volt and minus 9 volt, and both we are going to limit the current to 900 milliamps and minus 900 milliamps. So now we turn this on, and we will choose a sinusoidal. This sinusoidal with 10 kilohertz, and our amplitude or our peak to peak is 1 volt, which means your amplitude is 0.5 volt or 500 millivolt. There is no offset. You can uncheck this box, so because there is no offset. Now let we run the signal. Now it's running, and we will go to the scope and choose channel 1 and channel 2 only. So just keep channel 1 and channel 2 and uncheck these boxes for channel 3 and 4. Now run. Okay. Now, as a first step, the first step to do is by clicking on auto set. So, and now we need the offset, and just keep this 500. You can see, this is your input and this is your output. So it amplifies your input almost 4 times. Your gain is negative R2 divided by R1. So if you divide 20 kilo ohms by 5.1, or theoretically 19.82 divided by 505. So it's almost 4, less than 4, maybe 3.9 something. And negative means, as you can see, there is a phase shift between the input and the output 180 degrees. This is what negative means, because we have used pin 2, which is inverting op amp. Let we adjust this to, let me do it 20. Okay, now, good. Now we can measure our variables, which are maximum, minimum, frequency. Let me see what we should measure. This is peak to peak. We're gonna to measure peak to peak, maximum frequency. So you can choose any, but our box is click on measure, and for channel one, we want to add, for channel one, we need to measure the maximum, and we need AC RMS also, because the root mean square. For sinusoidal, it's maximum divided by root 2. Also, we need peak to peak. What else? You can choose any, but this is what we need so far. For the horizontal, we need the frequency, and we need, let me do it period, which is 1 over F. And then go to channel 2. Also choose, for channel 2, we need maximum, we need AC RMS, and we need peak to peak, we need, what else? This is 1, 2, 3, 4. Okay. Now we need also frequency, and what else we need? Let me do it period. Okay. Now, as you can see, it your maximum is 505 for channel 1, which is your input, and here is almost to 1.99. So it amplifies your signal 4 times. The amplification, it depends on your feedback resistor and your input resistor, which are R1 and R2. R1 is your input resistor, and R2 is your feedback resistor. So R2 divided by R1 is your amplification. This is for the first part. Now, let we go to the second part, which is non-inverting amplifier. So what you can do, only switch your input. That's it. So here, turn this off. So this is your input was connected to pin 2, right? So just move this to ground, and R3 will be now your input. Now, let me see what we will get. Now, just want to make sure that everything, yeah, it's on, and this is running. So what we will do, auto set to see. You can see now there is no phase shift, right? And it amplifies more than it's around 2.5 because now your amplification is 1 plus R2 divided by R1. 1 plus your feedback resistor divided by your input resistor. You can see here your maximum is 2.47 and your input is 510. So it's 2.4. So if you do your calculation, you can find that your amplification is 2. I think 45. It's 1 plus R2 divided by R1. That's all for today. It was only to introduce you by the inverting and non-inverting op amp. Thanks for watching and see you next class.